Good morning, my YouTube viewers. It's Crystal here. I haven't made a video in, I would think, at least a week because I've been very sick. My boyfriend, he went to a football drinks and he picked up a virus there and he passed that on to me, so I was sick from that virus and I was just about recovered from that virus. And I went over to my boyfriend's mother's house and she had a virus. She didn't tell us she had a virus until we already got there. And my boyfriend and I couldn't leave because we had caught a lift with somebody. So she passed that virus on to me. I have COPD. People who watch my videos know that. It just about killed me. And so I've been really sick with that. But this morning I feel well enough to make a video. So I do apologize if my voice isn't 100%. I'll try not to cough. But I really did want to make this video. I was like working on it a little bit when I was sick. But obviously I couldn't work a lot on it because I was too sick to do anything. So the title of this video is going to be Learn Statistics with R using the IRIS dataset. And the IRIS dataset is inbuilt into R. So I have used Kaggle's notebook because in Kaggle's notebook you can use either Python or R and you decide which language you want to use. And I decided to use R. The reason why I did that is because data scientists are supposed to know Python and R. From what I understand, they do use Python for work and R for research. So I do have to say that I prefer Python, and the reason why is because I can use it with Google Colab. R, I don't have an R interpreter, and so you can use it with Replit, but Replit doesn't turn out as nice as Kaggle's Jupyter Notebook. So I decided in this instance, since I was going to make a video and a blog post out of it, I was going to use Kaggle's Jupyter Notebook in the R programming language, which is what I did. So one of the great things about R is it has inbuilt datasets. So we're going to use the IRIS dataset. I went through a lot of R's datasets and they're a bit obscure, but the IRIS dataset is a dataset that almost everybody knows about. So I decided to go ahead and use the IRIS dataset. So the IRIS dataset consists of 50 samples from each of the 3 species of iris, being Setosa, Virginica, and versicolor. 4 features were measured from each sample, being the length and width of the sepals and petals. The IRIS dataset is a typical test case for many statistical classification techniques in machine learning. So that's why we're using the IRIS dataset, because it's widely known, widely used, and it's typical. So this is your IRIS dataset. This is what it looks like. So you can see sepal length, sepal width, petal length, petal width, and you can see these species. So what you have to do is you have to convert the species to a number. You have to like encode it. It's like ordinal encoding in Python. So we use the code s.numeric to create a new column and call it iris species num. So we have a new column. So instead of the species being there, hold on a second. So instead of having the species, you're going to have the number, and that's what we're going to be using, the number. Now what we're going to do is we're going to create a histogram of the species num. So it says 1, 2, 3. A histogram is a graph that shows the frequency of numerical data showing rectangles. The height of the rectangle represents the distribution frequency of a variable. So there's your histogram. Now we're going to create a bar plot using iris petal length. A bar plot represents an estimate of a central tendency for a numeric variable with the height of each rectangle and provides some indication of the uncertainty around that estimate using error plots. So now we have a bar plot of the petal length, and you can see that each species of iris has a different petal length. So now we're going to create a pie chart. A pie chart is a circular statistical graphic which is divided into slices to illustrate numerical proportions. So this shows you how to create a pie chart in R, and we're going to be using species num. We check the dim, and that's sort of like shape in Python. So you have 150 rows by 6 columns. We summarize iris, so that gives you your 5 values of your minimum, your first quarter, your median, your mean, your third quarter, and your max. So that's a summary. It's kind of like describe in Python. Now we're going to check the measure of center. The measure of central tendency is a summary measure that attempts to describe a whole set of data with a single value that represents the middle or center of distribution. So we're going to check the mean, and the mean refers to the average of a set of values. So we check the mean, which is the average. We're going to check the median. The median is the value separating the higher half from the lower half of a data set. So now you've got your median. Now what we're going to do is we're going to check the measure of dispersion. We're going to check the range. So the range is the spread data from the lowest to the highest value in the distribution. It is the simplest measure of variability. So there's your range. We're going to check our variance. Variance is the expectation of the squared deviation of a random variable from its population mean or sample mean. Now we're going to check standard deviation. Standard deviation is the square root of a dataset's variance. So we've got the standard deviation. So now we're going to make a stem and a leaf chart. A stem and leaf display is a device for presenting quantitative data in a graphical format similar to a histogram to assist in visualizing the shape of the distribution. So the only one that I could get a decent stem and leaf display was this one here. So it's going to be number 3. So number 3 is the iris petal width. So that's the only one where we got a decent display. Everything else was zeros, except that. Now we're going to do a histogram again, and we've already discussed histograms, so we're not going to discuss it again. But this particular histogram has a kernel density estimator in it. So you can see this is your histogram of your petal length, the histogram of your petal width, histogram of the sepal length, and histogram of the sepal width. And now we're going to create a box plot. The box plot is a method of graphically demonstrating the locality, spread, and skewness groups of numerical data through their quartiles. So now you can see how you can make a box plot in R. We're going to create a scatter plot. A scatter plot is a type of plot using Cartesian coordinates to display values for typically two variables for a data set. So you can see we've made scatter plots. Now we've got a pair plot. And so that looks really good. That's just paired scatter plots. That looks really good. Now we're going to do something called a strip chart. A strip chart is a one-dimensional scatter plot of a data set. They are a good alternative to a box plot when the sample sizes are small. So this is your strip chart. We've got a strip chart of the sepal length, a strip chart of the sepal width, a strip chart of petal length, and a strip chart of petal width. Now we're going to be talking about linear regression. Linear regression analysis is used to predict the value of a variable based on the value of another variable. The dependent variable is the variable to be predicted on, and the independent variable is used to measure the prediction. This form of analysis estimates the coefficients of the linear equation involving one or more independent variables that best predict the value of the dependent variable. So just a second, I've got to write down something. Okay, so there's your linear regression. Now we're going to check the coefficients. The coefficient is a multiplicative factor in some term of polynomial, a series, or an expression. When the coefficients are themselves variables, they may be called parameters. So, and now we plot it on a graph, and so you can see how the linear regression has been plotted on a graph, and we've done that for the petal width, the petal length. We get a summary. So a summary tells you about that particular linear regression, and we're also going to check the intercept, because that's another thing that is checked in linear regression. The intercept is the expected mean value of y when x equals 0. So that's what I've got for the intercept. Now we're going to check the linear model. Said linear models describe a continuous response variable as a function of one or more predictor variables. So here's your linear model. Looks great, doesn't it? Gives you your intercept, gives you your summary. And now we're going to check it with the AIC. That's the key information criterion as an estimator of prediction error and theory, thereby relative quality of statistical modes for a given set of data. Given a collection of models for the data, AIC estimates the quality of each model relative to each of the other models. This AIC provides a measure for model selection. So it's like a goodness of fit test. So you can check your AIC here. Now we're going to check the central limit theorem. And so basically what the simple limit theorem is it doesn't matter what kind of a model that a distribution that you have. If you sample the distributions enough, the mean of those samples are going to resemble a normal distribution or a bell curve. But I will read to you what I've written about this. The central limit theorem establishes that in many situations, when independent random variables are summed up, their properly normalized sum tends toward a normal distribution, even if the original values themselves are not normally distributed. So that's your central limit theorem. So we're going to sample it 5 times so you can see what the mean is when you sample it 5 times. Now we're going to sample it 30 times, and you can see that the mean when you sample it 30 times more closely resembles a bell curve. So now we're going to talk about the confidence interval. Confidence interval is a range of estimates for an unknown parameter. The confidence interval is computed at a designated confidence level, the 95% confidence level being the most common, but other levels such as 90% or 99% are also used. So there's your confidence interval. Now we're going to do the proportion test. Proportion tests can be used for testing the know that the proportions probabilities of success in several groups are the same for that they equal certain given values. So we did the proportion test, and you can see that this is your proportion test. Now we're going to check the binomial test. The binomial test is a test used in sampling statistics to assess whether a proportion of a binary variable is equal to some hypothesized value. So that's your binomial test. Now we're going to check the chi-squared test. The chi-squared goodness of fit test is a statistical hypothesis test used to determine whether a variable is likely to come from a specified distribution. It is often used to evaluate whether sample data is representative of the full population. So there's your chi-squared test. Now we're going to check the t-test. Students' t-test is a method of testing hypotheses about the mean of a small sample drawn from a normally distributed proportion when the standard deviation is unknown. So here's your students' t-test. So we're going to use regression analysis. Regression analysis is a set of statistical processes for estimating the relationships between a dependent variable and one or more independent variables. So here is your regression analysis. So when you do your regression analysis, there's also a predict function. So you've got your new iris, and then they give you some values for the sepal width, the petal length, and the petal width. It doesn't give you the value for the sepal length. And then so you predict on the sepal length, and it tells you the sepal length is 5 and a bit. So you can actually make predictions as well. Now we're going to check the analysis of variance. Analysis of variance, or ANOVA, is a collection of statistical models and their associated estimation procedures used to analyze the difference among means. So here's your analysis of variance. We're going to check the Shapiro test. The Shapiro-Wilks test is a test for normality in frequentist statistics. So there's your Shapiro-Wilks test. And we're going to check the Tukey test. In the Tukey test results, the formula indicates how large an observed difference must be for the multiple comparison procedure to call it significant. So that's it, I think. I think that's it. That's all of the statistical values that I put in this blog post. And so if you want to know statistics in R, well, this is giving you a lot of statistical formulas that you can use. And you can learn a little bit about statistics. And I intend to make a blog post on this as well. And I will let you know when the blog post is finished. So thank you very much for watching my video. Thank you to my subscribers for supporting my channel. And I look forward to making more videos for you in the future.